All right, so here we're going to talk about how ionic bonds are actually formed. We've talked about this general word transfer before, and I've drawn arrows just around general circles, but there is a proper way to draw Lewis dot diagrams for these ionic compounds that are being formed. So this is what we're going to do now, and this is going to be completely different than covalent because we're not sharing electrons, which means these diagrams are going to look different. So at the top of the page, you've got these steps broken down. And really what you're going to be doing in the future in general is really going to come down to those three big steps. But I wanted to add some clarification and explain what we do and how we do each of these steps. So you got plenty of information there to get you going. So what you're going to do to start with is draw one Lewis dot diagram for each of the elements involved in this ionic bond separately. So you're going to have to look at the periodic table. Remember that the title or the kind of column number that has an A next to it tells you how many valence electrons each of our elements has. So oxygen has 6, carbon has 4, and so on. So that's how many valence electrons we have, and we're going to put that many dots around our element's symbol. And remember, when we're placing these dots, let's say I was doing sulfur, which it's 6 dots. We're going to put 1 dot on each side before we go back and double up. This is going to be really important because we need to see where we have these empty spaces, and it's important that they're on separate sides instead of just being on the same side. So there is a difference between these, even though they both have 6 dots. We need to make sure to put those dots out correctly for each element. And honestly, at this point, I've asked you to draw one of each element because a lot of you struggled with writing formulas. But if you were good at writing ionic compound formulas, then writing the formula for the compound that the element's going to make is actually going to tell you how many of them you're going to need. Because as a little preview, later on, we might have to draw more of each of these atoms if we end up running out of spaces and electrons. So it might be helpful if you write the formula to start with and draw that many atoms, at least to know how much space you're going to need to draw these in, and then you can get going. But it is not required for you to be able to write formulas for you to be able to do this process. It's just going to be a little bit more of, I wouldn't say guess and check, but just you draw it and then you need more of this and then more of that, and you keep going until it all works out and evens out. So we start by drawing our elements, Lewis dots, separately, and then our step 2 is going to be to draw arrows to show our electrons being transferred. And they're always going to move from the metal to the non-metal, and every atom is going to get completely full with 8 valence electrons or become completely empty with no valence electrons visible. And it's really important as we're drawing them that we are very specific with the arrows. These aren't just telling us a general direction. It's very specific, taking this specific electron, moving it into this specific space. And I'll show you that in these examples we're going to do. And this is where I pointed out, if as we're drawing arrows, I don't get all my atoms completely full or completely empty, if I have some leftover spaces or if I have some leftover electrons, then I'm going to have to draw another atom to get more of what I ran out of. And then finally, we're going to redraw those atoms that the arrows drawing didn't actually erase the dots and move them. We're just kind of making a plan there, drawing arrows, showing where the electrons are going to move. And then step 3 is where we actually redraw those same elements, those same symbols that we had before with their new electrons. So at this point, everyone should be completely full and completely empty. We are going to put them in square brackets, and then we're going to write their charge in the top corner, like a +1 or a -1, based on how many electrons they've either gained or lost. Remember that atoms become positive if they're losing electrons, and they become negative when they're gaining electrons, but we already are kind of familiar with those charges, the normal charges that elements get according to their location on the periodic table. So you can also use those because those should be the charges they become after they've gained or lost electrons. This is just kind of reinforcing that idea and where those charges came from. Now, in this third step, we can use a coefficient, just a big number in front of the ion, if we needed more than one. So up here, we did have to draw multiple atoms of each, just to make sure we had enough dots and had enough spaces. But once we know exactly how many we need, and we've shown that transfer with those arrows, then we can kind of simplify it again, so we don't have to draw quite so many atoms. So let's go ahead and see some examples of this, because I think it makes a lot more sense once you see it happening. So this first one is going to be pretty simple, but it is going to at least get you understanding what I want you to do with each of these steps. So in this first example, it asks us to draw the process of formation of an ionic bond between sodium and chlorine. So we're going to start by drawing a Lewis dot diagram for sodium and for chlorine. If we check the periodic table, sodium is in column 1, which means it gets 1 dot. Chlorine is in column 17, or 7A, which means it gets 7 dots. That's our first step, just drawing one of each. Step 2 is going to be to use my arrows to show the electrons moving from the metal, which was our sodium, to the nonmetal. This will also always be the one that has less to the one that has more, because we want to move as few electrons as possible. So I'm going to take this one from sodium and move it specifically into this space on chlorine. This one space here on this one side that doesn't have 2 electrons. So very specific, starting at a specific electron, moving into a specific place on the chlorine. Now I need to ask myself at the end of step 2, or after I've done that, are all my atoms going to be completely full and empty? Well, yes, after I got rid of that and filled in this space, it looks like they will be. So we're ready to move on to step number 3, where we redraw these same elements, so my sodium and my chlorine, with their new electrons, which means chlorine is now going to be completely full, and that sodium is now completely empty, no dots around it. Put them each in square brackets and give them each their charge. Sodium is a +1, chlorine is a -1, either because I know everything in the first column is a +1, or, like we said before, losing electrons makes us positive, and since sodium lost 1 electron, it becomes a +1. Gaining electrons is negative, gaining 1 electron made chlorine a -1. So this is that full process of formation of the ionic bond between sodium and chlorine. Not too bad, I hope, but we need to show each of these steps. Somewhere along the line, maybe on the CBA or a final exam, they like to ask what it would look like in the end after the ionic bond forms, but we need to practice drawing the full process because we don't know if they might ask you about the beginning of the process or the end of the process. So let's do another example together. The second example just changed the elements. The whole kind of wording of the problem is still the same. If we want the full process from beginning to end, we got to ask you for the full process. So start the process again. Potassium and oxygen this time. Potassium has 1 dot again, just like sodium did. Oxygen is going to have 6 dots. You'll notice that I've kind of taken a shortcut because I knew there were going to be 6 dots. I knew 2 sides would have 2 dots on them and 2 sides would have 1 dot on them. So I just drew them out in that order because I knew that's what it was going to end up being. So now I need to draw my arrows from my metal to my nonmetal, so from potassium to oxygen. And this looks a lot like what we did with sodium and chlorine, except that oxygen still has this little empty spot over here. I'm double checking, and I'm sure potassium only has 1 dot to give oxygen, so we're not done yet. I'm going to need another electron to fill in this space, but I've run out of electrons from this potassium, which is why I'm going to have to draw another potassium atom so that I have enough electrons to fill in my spaces. And this is where I had said before that in that first step, or kind of before you started moving arrows and electrons around, that you could write the formula. If I checked the formula, and in order to write this, we would have to find our symbols and charges and then cross drop reduce, then I would have already known that the formula for potassium oxide is K2O, which reinforces why I've got to have two Ks here in order to get oxygen all full and happy with its 8 valence electrons. It'll always occur in that ratio because of those charges. So, knowing that ahead of time, I could have already drawn out that extra potassium instead of doubting myself and rechecking my valence electrons. So, sometimes that can be helpful, but you don't have to. You just have to add whatever you need in order to get all of our elements, atoms, full and happy. So, at this point, it looks like we've got a plan. Everything's going to be completely full and completely empty. So, let's redraw our elements, potassium and oxygen. Oxygen is completely full now, and the potassium is completely empty, and we can put them in square brackets with their charges. And this is where I had said you can put a coefficient up in front of any atom that you needed to draw more than once over here. You could also just write 2 of these K's out. It's not that hard, especially when they don't have all those dots around it, but it's simplified, and sometimes other people will write it this way just because it's simpler and easier to understand. So this works, and I think making our job a little bit easier, a little bit shorter isn't a bad idea. Okay, let's move into that third example. Here it tells us to draw the formation of the ionic bond between fluorine and magnesium. If I check, fluorine has 7 valence electrons, and I'm going to strategically put that empty space facing magnesium just because I know I'm going to have to draw arrows moving these electrons towards each other. So this is the one time, I know y'all have seen me draw these diagrams the same way over and over again. I normally do like top around to the side, and they look the same all the time, but this is where I strategically decide, it doesn't really matter which sides these dots go on. I'm going to put them on the sides that are going to make my job, my arrows, a lot simpler and easier. So, got my original atoms drawn out here. Time to draw my arrows, and be careful. All of these other ones, I've been drawing them from the left atom to the right atom, but it's always metal to non-metal. So here I actually purposely gave you fluorine and magnesium in that order because we're not going to be drawing arrows this way. We're always going to draw them from the metal, which was magnesium in this case, to the non-metal. So magnesium to fluorine, and now it looks like fluorine is full, but I still have an electron on magnesium, so I probably need another fluorine. Once again, I'm going to strategically leave the side of my fluorine where I'm going to be moving this electron empty, facing that magnesium, and that looks good now, so I can redraw these as completely full and completely empty. Fluorine is going to be full, square brackets there. Magnesium just gets to stay empty. It's a +2, and those 2 fluorines are each a -1. So hopefully that's not too bad. In these next few examples, number 2 is going to be a little bit big and kind of bulky. There's going to be a lot of atoms there. If you write the formula beforehand, then you will kind of realize how many of each you need, but you might well want to kind of do it all the way over here, just like draw an arrow. Most of these others you can fit in this space, but the aluminum bromide it's number 3. Barium and nitrogen, that's going to be pretty big and kind of bulky, so you might choose to do it over in that space and write that formula, kind of see how many of each thing you're going to need ahead of time so you don't doubt yourself. But I hope that's not too bad.